Almost all of the numbers we will use in chemistry represent some physical value. That means most of our numbers can't stand alone. They have to have some sort of unit associated with them. Scientists use the metric or international systems of units. So let's take a little time and talk about those now. In this video, you'll learn about the base units used in both the metric and international or SI systems. The base units are carefully defined, and when a measurement is particularly large or small, the base unit can be modified with a prefix. At the end of this video, I'll briefly discuss the definitions of some of the base units. The measurement system most commonly used in the US is referred to as the British Imperial or US customary system. This includes units like inches, feet, cups, gallons, pounds, those sorts of things. In order to convert between units, you have to have a specific conversion factor. For example, if you wanted to convert a length measurement, you might need to know that there are 12 inches in a foot, or 3 feet in a yard, or 5,280 feet in a mile, assuming that we're using standard and not nautical miles. Most countries around the globe use the metric system for their everyday measurements. The major benefit of the metric system over the US customary system is that it is decimal based. An object that's a few inches long can be measured in centimeters. You can measure your height in meters, and the distance you travel to the store can be measured in kilometers. The meter is the base unit of length, and centimeters and kilometers can be converted into meters using only factors of 10. The metric system became popular around the time of the French Revolution, and for a long time, you could go to Paris and see the actual physical objects that defined a meter and a kilogram. We'll talk about that more towards the end of the video. The international system, which is usually abbreviated as SI, those units were born out of the metric system. A few of the base units are modified metric units. We'll talk about those differences shortly, but most of the base units are the same as those in the metric system. In 2019, several international groups of scientists agreed on a new set of definitions for all of the base units using a handful of universal constants like the speed of light. Again, details for that will come at the end of this video. There are 7 base units in the metric system. We're really only going to worry about 5 of them. Every other unit of measurement is a derived unit, which means it is some combination of base units. To measure length, both the metric and SI systems use the meter as the base unit. 1 meter is a little bit longer than a yard. If you wanted to measure an area or a volume, you would use a derived unit based on meters. So to measure area, you would measure in square meters. If we were going to measure a volume, we could use cubic meters, or we could use liters. Both of those are derived units. A liter is defined to be 1,000 cubic centimeters, which is roughly a quart, and so that is why we call a liter a derived unit. When we're measuring mass, the metric base unit is the gram. Now, a gram is really, really tiny. It's about the mass of a paperclip or a thumbtack. In chemistry classes, most of the masses we're going to deal with will be less than 200 grams, which works pretty well using the gram as the base unit. The SI system is used in all sciences and all types of engineering, though, and the measured masses tend to be much larger. For this reason, and for historical reasons, the SI system uses the kilogram, which is about the mass of a pineapple, as a base unit. Now, the main issue that I personally have with the kilogram as the base unit is that kilo is a prefix. For our purposes, we will consider base units to be those that don't have a prefix attached to them. That just simplifies things a little. One other thing I want to point out here is the difference between weight and mass. Technically speaking, the mass of an object is based only on the amount of matter it contains. So an astronaut has the same mass on Earth as she does on the moon. Weight, on the other hand, combines the mass of an object with the force of gravity that's acting on that object. And so our astronaut weighs less on the moon because the moon has a lower gravity. Since most of us don't spend time outside of Earth's gravitational field, we use the terms mass and weight interchangeably. I'm guilty of this as well. So whenever I say weight in this course, consider it to be a mass. Measurements of time are the one area where the metric and SI systems don't follow a strictly decimal pattern. The base unit of time is the second, and longer times are typically measured in hours, minutes, days, etc., just like you would expect. The conversion between these units aren't as neat as most metric conversions, but they do have the major advantage of being familiar to most people. For time frames that are shorter than a second, the decimal prefixes are usually used. Seconds are really the smallest amount of time that we talk about in our daily lives. So it makes sense for the second to be used as the base unit of time. There is a separate video in this module that covers temperature scales, but briefly, the US measures temperature in degrees Fahrenheit most of the time. The metric base unit for temperature is the degrees Celsius. While water freezes at 32 degrees and boils at 212 degrees on the Fahrenheit scale, its freezing and boiling points on the Celsius scale are 0 and 100 degrees, respectively. The problem with the Celsius scale is that using the freezing point of water as the 0 point is really arbitrary. Nothing magical happens at 0 degrees Celsius. There is a temperature, though, that is really special. The temperature that is measured on a thermometer is really a measurement of how fast atoms are moving. At a temperature that we call absolute zero, the atoms in any substance aren't going to be moving at all. Absolute zero is the coldest temperature that could possibly exist. The SI base unit for temperature, the Kelvin, incorporates the idea of absolute zero. So 0 kelvins is in fact absolute zero. Kelvin temperatures cannot be negative, whereas Celsius degrees can certainly be less than 0. The last base unit that we use in chemistry is the mole. A mole measures an amount of substance by counting its individual atoms or molecules. It's sort of like a dozen, except it's much, much larger. We will go into a lot more detail in moles in a later module. Each of our base units has a standard abbreviation. Remember that the metric system relies on prefixes to change the size of the units. Each prefix is going to have its own abbreviation, and you'll usually see units given in a two-letter shorthand. The prefix abbreviation will be first, followed by the base unit abbreviation. Let's talk about these metric prefixes for a bit. Remember that a meter is roughly the same length as a yard. If you wanted to measure, say, the width of a pencil, you'd probably use inches and not yards. In the metric system, we can use prefixes to change the size of our units. So instead of measuring the width of our pencil in meters, we might use centimeters, which are 1/100th of the size of a meter. It is important to be careful when you're writing abbreviations for modified units. First of all, capitalization can change the meaning. And we'll talk about that shortly. And secondly, you always want to write the prefix abbreviation before the unit. You'll see on the next slide and the one following that, there are an awful lot of M's in the metric system. M can represent meters, but it can also represent the prefixes mega or milli, and we don't use it by itself to represent micro, but it's in there too. Being careful with the order in which things are written and the capitalization helps us avoid confusion. The prefixes are usually listed with associated exponential values, like 10 to the third or 10 to the negative ninth. These values tell us how many standard base units fit in a single modified unit. Positive exponents mean that our units have gotten larger, and negative exponents mean that our units are smaller. The five most common prefixes used to make larger units are listed here from largest at the top down to the smallest. You've probably seen distances measured in kilometers. The storage on your phone is typically measured in gigabytes these days. To use these prefixes, remember one modified unit is equal to 10 raised to the appropriate power of base units. So, for example, a kilometer is 10 to the third or 1,000 meters. I do want to point out that all of the prefixes except for kilo that are listed on this slide. So all of our prefixes that make our units larger, except for kilo, are represented with a capital letter. For tera and giga, it's not super critical. I mean, it is because that's how we do things, but there's less confusion involved for tera and giga. But peta and mega, which are abbreviated with a P and an M, share those abbreviations. For example, milli, which is a prefix that indicates 1/1000th of something, is a lowercase p. I'm sorry, and pico is a lowercase p. Now, to make our units smaller, we're going to use this set of prefixes. Centi is the only prefix on our list at all that has an exponent that's not divisible by 3. The prefix centi comes from the same root as the word century. A century is 100 years, and a centimeter is 1/100th of a meter. The other really unique prefix here is micro. Micro has 2 abbreviations, and neither one of them are a simple single commonplace letter. Again, that's because we've already used the capital M and the lowercase m as prefix abbreviations. So micro can be represented with a lowercase mc. That's used in many health science applications. So you might see vitamin tablets that contain 25 mcg of active ingredients. In physics and engineering, a lowercase Greek mu is used for micro. It's that second abbreviation shown that sort of looks like a lowercase u with a little tail coming off on the left. It is perfectly acceptable to use either of those abbreviations. Now, in the examples that I have here, I used the mu to represent the micro prefix to modify the units of kelvins. I could have used MC capital K just as easily. Now, in the video on dimensional analysis, I'm going to show you how to use these definitions to convert units. But for now, we just need to be familiar with what they mean. In our remaining time, I'm going to give you guys a little history about the metric and SI base units. The meter was first defined by a French committee in 1791 to be, quote, equal to 1/10,000,000th of the distance from the North Pole to the equator, so the quadrant of the Earth's circumference, measured along the meridian passing through Paris, end quote. Soon the first prototype meters were crafted out of platinum. They were bars that were exactly 1 meter long. In the late 1800s, new prototypes were produced from a platinum iridium alloy. These standards, like the one shown in the lower picture, were longer than a meter, but they were marked very accurately. That way, if the end of the bar was worn, it wouldn't affect the measurements based on that standard meter. In 1960, the prototype meters became obsolete. The meter was redefined at that point in terms of the wavelength of one specific radiation coming from one specific type of krypton atoms. As I mentioned before, the origins of the metric system were tightly connected to the French Revolution. In 1791, at various places around Paris, representative or provisional meters were installed on the sides of buildings. The picture in the upper right here is the last remaining provisional meter in its original location. And this is across from the Palais de Luxembourg in Paris. Once the meter was defined, a kilogram was defined to be, quote, the absolute weight of a volume of pure water equal to a cube of 1/100th of a meter and at the temperature of melting ice, end quote. Much like the standard meters, standard kilograms were made out of platinum. They were stored under vacuum at various laboratories around the world. After 1960, the kilogram was the only metric unit defined based on a single physical object. There was 1 kilogram, also in Paris, that was defined to be the kilogram. All of the kilograms at other laboratories were copies of the original kilogram. In 1989, scientists discovered that the standard kilograms around the world, which originally in 1889 had masses identical to that of the kilogram in Paris, now had masses that varied by up to 50 micrograms from the Paris kilogram. This was a problem. The International System of Units was officially published in 1960, although work on the system began shortly after World War II. The original definitions of all 7 base units were based on various physical phenomena. Over time, the definitions have become more specific, and by the end of 2019, each base unit was defined in terms of accepted universal constants. This graphic includes all 7 SI base units. The A stands for amperes, which measures electrical current, and CD represents the candela, which measures brightness. The second has been defined in terms of radiation from a cesium-133 atom since 1967. When you hear references to atomic clocks, those devices are based on this type of cesium. Since 1983, the meter has been defined based on the speed of light in a vacuum. Kilograms are now defined based on a constant that relates the frequency of light to its energy. The constant has a very specific finite value, and in combination with our accepted definitions of seconds and meters, the definition of a kilogram can be found. The last base unit that we'll worry about right now are kelvins. And kelvins are based on a constant that relates the speed of a gas molecule to its temperature, along with the definitions of seconds, meters, and kilograms.